Welcome to Lecture 3 of Networks, Friends, Money and Bytes. In today's lecture, we will continue to talk about Google, but this time how Google rank web pages. In the last lecture, we talked about how Google auctions the advertising slots, usually on the right panel of the search results. And today we'll talk about how Google ranks the web pages displayed in the main panel of the search result page. And we will see that the algorithm that Google uses to rank these web pages can be viewed as the solution to a gigantic system of linear equations. So while in this lecture we'll start using some linear algebra and matrix notation to accelerate the presentation, you should know that at the heart of all these notation, it is just solving linear equations. Now, the idea that links can be embedded in text dates back to at least the middle of last century. But then in the 1990s, with the introduction of the web in '89, the browser in 1990, and the web portal in '94, this vision of linking text grew to a gigantic scale. Now we can view these web pages as a network. They form a network of information represented as web pages. So each node is a web page, and a link is what's called a hyperlink. It connects the text in one web page to that of another web page, and you go from this page to the other by clicking on that link. Now, as we all know that web page A points to web page B doesn't mean that B points back to A, so we have to provide a sense of direction to this link. We call this a directional link, and the resulting graph is called a directed graph. How big is this graph? It is very big. Nobody knows for sure, but it is estimated that N, the number of web pages out there, is somewhere between 40 to 60 billion. At the same time, this graph is also very sparse, meaning that there aren't that many links compared to the number of nodes out there. Okay. Many of these web pages have very few links pointing in or links pointing out. So we're talking about a huge and a sparse graph. It's a very special kind of graph. And the idea is that we will be able to leverage the pattern of connectivity in this graph to calculate what we call the importance score of each node. In this case, each node is a web page, and the importance score will be used to rank that page. And what we want to do is to say that let's turn a seemingly circular logic that says important nodes pointing to, say, you being a web page, means that you are also important. This argument almost sounds like a cyclic argument, but in fact we can use it to derive a recursive definition to define an equilibrium. Now, this equilibrium is not the equilibrium of a convergence of an algorithm like in power control, or the equilibrium of strategic thinking as in game theory. This is a fixed point equation equilibrium, as we will see in the rest of this lecture. Alright, so coming back to this question, how can we quantify the relative importance of different nodes in a graph? Or more specifically in this case, quantify the importance of each web page. We will see later in lecture 8 quite a few different ways to quantify the notion of importance of nodes in a graph. In today's lecture, we will look at a specific one used by Google. Now, there are quite a few intuitions you can think about this. One is to say, well, you want to quantify node importance, right? So maybe I'll just count how many links does this node have. Well, since this is a directed graph, where each link is directed link, I'll just count how many links point into this node. In this case, there are 3 links pointing into this node. So we call this the in degree. And the out degree is 1 because there's just one node, one link pointing out of this node. And the total degree of this node is 4. Okay, so this is a simple intuition, as we will see that it's sort of getting on the right track, but it lacks many elements for it to be a useful metric. Now, we will also see in the discussion of importance scores of nodes a recurring theme in this course. And that recurring theme says that whenever we talk about a network, whether it's a network of people, a network of web pages, a network of wireless devices, there actually are 2 different elements in it. One concerns the topology, that is the pattern of connectivity, and that's usually represented visually by graphs and algebraically by matrices. We will see within today's lecture 3 matrices to describe in increasing order of complexity the graph that we are dealing with. But that's only half of the story. The other half is the functionality that you would like to study that's running on top of this network. That's what you do on the graph. In today's case, what you do can be viewed as a special case of navigation or search. Later in lecture 9, we will talk about 6 degrees of separation. That's also a kind of navigation and search. In lecture 13, we'll talk about routing on the internet. That's another special case here. So in order to fully understand a network, we need to know not just properties of the topology, but also build models of functionalities. And in fact, in modules 3 and 4 of today's lecture, we will see some very crude model of the functionality of search and navigation that is implicitly assumed behind Google's ranking algorithm. All right, now back to our intuition. And that intuition says, let's count the number of links. We call that try number 0. It's the very basic intuition, and we will soon see that is hardly a very useful one when it comes to ranking web pages. Here's a little smarter idea that says what we can do is to say each node has a certain score. Give it a number. Give it a positive real number. Okay. We're going to denote that number as pi sub node index. In this case, say node 1. So it's got a number denoted as pi sub 1. And another node, say node 2, also has a number pi sub 2. Okay. And here's another one. Node 3 with a number pi sub 3. And our job for the rest of this lecture is to compute these pi's, what we call the importance scores. We can collect them into a vector, pi 1, pi 2, dot, 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 up to pi sub n. This is a very long vector, and by convention it's a column vector. We call this vector pi. Okay. In the textbook or in written media, printed media, you can use boldface. It's hard to draw boldface on the screen, so we're going to just use this arrow to represent that vector. So pi vector, that's what we want to compute. So try 1 says that, look, you got these pi's. Okay. Maybe you can just add up the pi's that points to you. For example, if node 1 and node 2 both point to node 3, then I can say node 3's importance is the sum of pi 1 and pi 2. Okay, simple enough. This is slightly better than just counting degrees because I now allow each node to have different importance score. Okay. And of course, in general, first node and second node, they may have many other connections coming in and going out. So this is a reasonable choice. Okay. However, what it ignores is that some node, like this node 1 here and 2, they are pointing to many other nodes, not just node number 3. So think of a professor who writes reference letters for her students. And if this professor keeps writing that this is the very best student I have ever had in my 80 years of teaching at this university and so on, if every student she writes in that way, and she writes like, say, 100 letters every semester, then soon people will realize that, hey, this professor's reference letters should be discounted. And that's the idea here, is that you got to normalize by how you spread your importance score. If you point to too many web pages, then each of those web pages that you point to should not receive all your importance. And that is the idea that maybe I should look at the number of outgoing neighbors that I have. So if node 1 with importance score pi 1 points to 3 other web pages, okay, then O sub 1 equals 3, our degree is 3, and I should divide node 1's importance score pi 1 by O1. Okay. So I should be assigning just pi 1 over 3 to each of the 3 outgoing neighbors. And therefore, if you point to more nodes, each of them will uniformly receive pi 1 over, say, 5 instead of pi 1 over 3. And if you only point to one node, then that node receives all your importance score. So let's try number 2 now. Okay, the idea is that we're going to normalize by the spread of importance. It turns out that by this point, we're sort of close to what Google does. In the next 3 modules, we'll have to quantify this intuition and then provide 2 more enhancements. But we're getting there. Okay, the idea is that look at all the importance scores, add them up across the links pointing to you, but make sure you normalize by their outgoing number of links. Now you may wonder, if I have a node here, number 2 with importance score pi 2, I can write pi 2 as some combination of the importance scores normalized from the incoming neighbors. Now each of these, say this involves pi 1, can also be written as the summation of normalized importance scores from its incoming neighbors. So the question is, on the left hand side I will have pi 1, pi 2 and all the pi's. On the right hand side I also have all these pi's divided by their outgoing number of neighbors. So I got pi's both on the left hand side and right hand side of this, I guess, linear equation system. Can they actually make sense collectively? Is there a set of consistent scores pi? Is there a vector pi that can satisfy all these linear equations simultaneously? If so, then we have found a particular meaningful and self-consistent way to assign importance scores. If not, then we're in trouble. So the question now is, how can we modify this basic intuition in our try number 2 now in order to guarantee both the existence of such a set of consistent scores and an efficient way to compute these scores? But before we go into the general space, let's look at a simple very small example. There are only 4 nodes and 6 directed links. Nodes 1 and 2 points to 3, 3 points to 4, and then 4 points to back to 1, 2, and 3. Okay. Now, what is the intuition of the importance score vector pi, which should be a vector of length 4 here, if we assume that such a pi consistent set of scores actually exist? Here's one particular view. We can think of nodes 3 and 4 as collectively acting like a supernode. Okay, let's call this supernode 3 plus 4. And here's node 1, here's node 2. 1 points to supernode 3 plus 4, so does 2, and the supernode points back. Okay. So now, intuitively, you look at this supernode, you say, this supernode got 2 links pointing inwards, but each of these nodes 1 and 2 only has 1 link pointing inward. So intuitively, you think that nodes 1 and 2 should each has a smaller importance score than the supernode 3 plus 4. And furthermore, by symmetry of this graph here, nodes 1 and 2 should have the same importance score. And then the supernode 3 plus 4 need to distribute its score in some way between nodes 3 and 4. So at least we know intuitively that pi 1 should equal to pi 2, and each of them should be smaller than pi 3 plus 4, the supernode score. Okay, so intuitively, that's what we should anticipate. Now we can write down the math a little further and calculate in this small example very easily the result. Now first of all, you also notice that in this node 3 pointing to nodes 4, that says that basically all the importance score pi 3 that I may get goes into node 4. And node 4 only got this 1 incoming link. Right, so pi 4 should equal to pi 3, or pi 3 divided by 1, because there's only 1 outgoing link from node 3. And plus what? There's no other terms. There's only 1 link pointing inwards to node 4. So we can just say pi 4 equals pi 3, and pi 1 equals pi 2. Now once we know that, the job is very simple now. Let's say pi 1 equals pi 2, this number is x. Pi 3 equals pi 4, this number is y. Okay. Now we know that there is 1 link from node 4 pointing to node 1. Right? But this node 4 is actually pointing outwards to 3 other nodes. So what we can write down now is that x equals y over 3. Okay. This is x, x, y, y. So just by looking at this arrow, we can write down x equals y over 3. At the same time, we also know that x plus y plus y, so the summation of all the importance score need to be normalized. Let's say normalized to 1. Why do we need to normalize it? Because it doesn't matter what is the actual absolute magnitude. All that matters is the relative importance of one node relative to the other nodes. So now we got 2 equations. One says x equals y over 3. The other says by normalization 2x plus 2y should equal to, say, a constant 1. Now we got 2 variables in 2 linear equations. In this case, we got a solution. The solution is x equals 1 over 8 and y equals 3 over 8, which satisfies our intuitive understanding in the last slide. Now, therefore, what we're going to output is that we will say nodes 3 and 4 tie for position number 1, 3 and 4, and nodes 1 and 2 tie for position number, I guess, 3, because positions 1 and 2 are tied between nodes 3 and 4. So you can display 3 and then 4 and then 1 and then 2, for example, on the search result page by Google. Now, is this the right answer or not? That's actually a tricky, almost philosophical question. What is the right answer? In some sense, the right answer depends on how does each user find the Google search results useful or not as useful. Now, because Google is such a dominant force in the search space today, it's actually hard to imagine what other search order might look like. So it's not easy to actually falsify whatever we might conjecture about that. And it is just very hard to measure or quantify subjective view on the usefulness of the search results. Okay. So what we are doing here is really a proxy of the real problem, which is make each individual users find the search results as useful as possible. And furthermore, as you can see that we carried out a whole bunch of computation. Well, in this case, it's not that much, 2 variables and 2 linear equations. But the actual numbers of these important scores are not displayed in the search result page. All you see is the rank order. You do not see the scale behind the order. So order is displayed. Scale, the numerical scale, is hidden from user's view. So in that sense, scale is really a means to the ends. So we don't know, for example, that this node is 3 times more important than that node. Now, these are some of the interesting caveats as we try to understand the true meaning of usefulness of the search results. But for the rest of this lecture, we will just focus on computing this scale now, which translates as a special case into the order of presenting these results on the search result page. So now we have seen a very, very small example. The question is, can this computation be generalized to an arbitrary structure of the graph? And furthermore, can we efficiently compute when the graph becomes very big?